This talk is a little different than some of the other talks. I'm going to be talking about an artificial black hole. And a black hole should radiate something as predicted by Stephen Hawking. And I'll be discussing the observation of quantum Hawking radiation and its entanglement in an analog black hole. And this is the world's first observation of Hawking radiation in any system, of spontaneous Hawking radiation. So this work builds upon a rich theoretical background, starting with Bekenstein, who predicted that a black hole should have both entropy and temperature. Hawking then predicted that the black hole should radiate like a black body at the very temperature predicted by Bekenstein. And in making this prediction, Hawking combined general relativity with quantum field theory. So this semi-classical calculation is considered a first step towards achieving a theory of quantum gravity. But it would be very nice to check this calculation. The problem is that a real black hole, the effective temperature of the Hawking radiation is very low. For a black hole of a few solar masses, the temperature is less than a microkelvin, and that would very much be dominated by other sources of radiation in space, like the cosmic background radiation. So, however, perhaps a very small black hole could be found, and the Hawking temperature is higher the smaller the black hole. You could say the wavelength of the Hawking radiation is given by the diameter of the black hole. So a smaller black hole will have shorter wavelength, higher temperature radiation. So perhaps in the early universe, primordial black holes were created, very small ones maybe, or perhaps at the LHC, small black holes could be found. In the meantime, in 1981, Bill Unruh came up with the idea of making an analog black hole in the laboratory where sound plays the role of light. Now, there have been many systems considered for a possible analog black hole. Bose-Einstein condensates, superfluid helium-3, an electromagnetic waveguide, ultra-cold fermions, rings of trapped ions, light in a nonlinear liquid, exciton-polariton condensates, and magnons in a magnetic wire. On the recently, entanglement has become of interest. Hawking radiation is pairs. One particle comes out of the black hole, the Hawking particle, and the partner particle falls into the black hole. So it's very important to think about the entanglement of these pairs. And I wrote a paper a couple of years ago explaining how one could easily measure the entanglement, and I've implemented it here. So on the experimental side, my group has been studying this problem and only this problem since 2009. And we've made a systematic study where we've developed all the various techniques that we needed, including creating analog black holes and observing small numbers of phonons. And another area under experimental study is surface waves in water. This is a classical system, surface waves in water, but one can see analogs of stimulated emission. Particularly white holes are studied here rather than black holes. Also, nonlinear optical fibers are under active study, as are exciton-polariton condensates. So, getting down to the subject of Hawking radiation and its importance, there's what's called the information paradox. After Hawking made his prediction of Hawking radiation, he very soon pointed out that this makes a paradox, that say information is used to create a black hole, and then the black hole evaporates. So this is the event horizon of a real black hole. And here is the evaporation, the Hawking radiation coming out. So the Hawking radiation should have no information at all. So what happened to the information used to form the black hole? That's the information paradox. So there are many, many possible solutions to the information paradox that one can find in the literature. And one possible solution is that the entanglement carries the information, that the Hawking radiation is entangled with earlier Hawking radiation. But this entanglement would be caused by some unknown phenomenon of quantum gravity. Now, there's a problem with this solution to the information paradox, is that the Hawking particle is already entangled with its partner particle inside the black hole. Remember, it's pair production here. So there's not much entanglement left to carry the information. So to break this entanglement between these two particles, it's been proposed that there's what's called a firewall, that perhaps at the event horizon of the black hole there's a firewall, and that breaks this entanglement. And then there's the firewall controversy, to try and decide if there might or might not be a firewall. So how does this all relate to analog gravity? In other words, to the research I'll be discussing today. We saw this entanglement. We saw the Hawking radiation, and we also saw this entanglement showing that these elements in the discussion actually exist. So for now, so here's a real black hole. This is a photon, Hawking radiation, say, being emitted from the black hole. It has a positive frequency and positive energy, like the photons around us in this room. However, inside the black hole, the partner photon has a negative frequency and a negative energy. And so one can have a pair of these photons with zero total energy. And so this can happen spontaneously. These pairs can be produced from nothing in space, just in the region of the event horizon. One doesn't need a source of energy. So so Hawking predicted a thermal distribution of pairs, that we would have not just one specific frequency, but a thermal distribution. Now, so here's the analog black hole. This is what you're seeing here is a Bose-Einstein condensate. It's an elongated 1D system with around 4,000 atoms in it. And it's about 0.1 millimeters long. And if we consider, and the condensate is flowing from left to right. So on this side, it's flowing below the speed of sound, subsonic flow. And here, it's flowing supersonically. So if we consider a phonon here on the subsonic side, it can move forward against the flow because the flow is subsonic, and it has a positive frequency. However, on the supersonic side, a phonon directed against the flow is actually swept along with the supersonic flow. So in the lab frame, it's moving the wrong way, and it has a negative frequency. It's been Doppler shifted so much that the frequency is negative. And then it therefore has also negative energy. So we're considering pairs of these phonons with zero total energy. We would like, in order to be analogous with Hawking radiation, we would like for these pairs to be created by vacuum fluctuations. So what's the nature of vacuum fluctuations in a BEC? So here's a BEC with phonons. These phonons we created in this work, one of the works building up to observing the Hawking radiation. So here's a BEC with phonons. You're seeing this standing wave of phonons. And this is not vacuum, because when we say vacuum in this talk, we mean phonon vacuum. So this is not vacuum. Here's a BEC without phonons. So this is vacuum. So where are the vacuum fluctuations? One might say this BEC has some smooth macroscopic wave function. So where are the vacuum fluctuations? Well, if one looks closely at the BEC, you see it's composed of point-like atoms. So on top of one of these atoms, the density is essentially infinite. And in between the atoms, the density is basically zero. And in every realization of the experiment, there's a different configuration of these atoms. And these are the vacuum fluctuations. This is true. These fluctuations are there whether or not we have phonons in the BE condensate. It's still composed of atoms. So we're going to look for the creation of the pairs by these quantum vacuum fluctuations. Now, how does one detect this Hawking radiation? It's very weak. There are very, very few phonons, and it's a thermal distribution. It's not at some nice, well-defined wavelength or frequency. So it's been proposed in the literature that one can use the correlation function. So what one does is one considers 2 points, x and x prime, along this 1D system, and one computes the correlations between these two points. And we imagine that this horizon here should be emitting pairs. It should be emitting phonons, one going that way and one going this way. So if we're at equal propagation times from the horizon, sort of like equal distances, equal propagation times from the horizon, there should be correlations. Whether the points are close to the horizon or farther from the horizon, as long as they're equal times, there should be correlations. And so here's a plot of the correlation function versus x and x prime. And one should see this band of correlations. Each point along this band is a pair of points, x and x prime, which are equal times from the horizon. So this is how we observe the Hawking radiation. So experimentally, how do we create this analog black hole? Well, in order to, we use there's a step potential here, and the atoms flow over the step and are accelerated to supersonic speed, like flowing over a waterfall. So this is a laser beam, a blue laser beam, elliptical shaped laser beam, which is coming out at us, and it's been cut in half here by a knife edge and then imaged onto the condensate with high resolution optics. And then this is moved with a steady velocity to the side by a high resolution acousto-optic modulator for people who study condensates. So here it's useful to consider a reference frame where the step is stationary and the condensate is moving from left to right. Then we could picture the condensate coming from the left, pouring over the potential and being accelerated to supersonic speeds. In addition, there's imaging with high-resolution optics. And furthermore, there's a trapping laser beam, which is a red detuned laser beam, so it's an attractive potential for the atoms. I should have said this blue laser beam, because it's blue detuned from the atomic resonance, it's a repulsive potential, whereas this red laser beam attracts the atoms and holds them in this tube-like volume. And however, we want very low densities. It enhances the effect for various reasons. And so this beam is very weak. It can only provide about 10% of the force of gravity. So we need a magnetic field gradient to cancel gravity, so the atoms don't just fall. So here are some experimental numbers. Here on the subsonic side, outside the black hole, the speed of sound is 0.57 millimeters per second, and the flow velocity is 0.24 millimeters per second. So this is subsonic flow in this direction. Inside the black hole, the speed of sound is 0.25 millimeters per second, whereas the flow velocity is 1.02 millimeters per second. So this is very much supersonic flow. We can see that the system is one-dimensional, since the trapping frequency in the perpendicular direction here is 140 hertz, whereas the interaction energy between the atoms is 70 hertz. So this direction of motion is frozen out. One can also show that this system, even though it's 1D, is phase coherent over a very long length scale, vastly larger than the system. Although it's been claimed in a certain paper that maybe you don't need phase coherence to see this Hawking radiation. Furthermore, so here's an integrated profile of this image. So this is the density profile, and this is where we're going to see the Hawking radiation, and this is where we're going to see the partner particles inside the black hole. So we can zoom in on this horizon region. It looks like this, and it looks similar to the green curve, and the green curve is half a gray soliton, and it was predicted that the density should be like half a gray soliton. So we're going to discuss two experiments here. The main Hawking radiation experiment, where this potential is moved at a constant speed, and then a preliminary experiment where we're going to cause the horizon here, the potential, to oscillate. So in addition to moving at a constant speed, it's going to have an oscillation on top of it. And this is going to act like a piston, creating phonons traveling out of the black hole and also into the black hole. And this will let us see what the waves look like, these phonons, so we'll know what we're looking for in the Hawking radiation experiment. So first, in this preliminary experiment, this is what the correlation function looks like. So we see this wave-like pattern. This quadrant of the correlation function is correlations between points outside and inside the black hole. So this wave-like pattern are the correlated waves on the two sides of the horizon. And from this pattern, we could get a lot of information like the wavelength. We could get K. We are applying a frequency, and we can get the wave number. So we could trace out the dispersion relation outside the black hole and also inside the black hole. These black points are the negative energy waves. And there's a maximum K due to dispersion. The dispersion relation of a Bose-Einstein condensate is not like light in a real black hole. As far as we know, light has a linear dispersion relation at all wavelengths. The speed of light is constant at every wavelength. However, that's not the case for this Bose-Einstein condensate. So there's dispersion here, and so there's some maximum K where the waves are trapped, where the group velocity here is to the right. There's a positive slope, That means the waves are trapped in here. They can't reach the horizon. So that only goes up to some certain k value. And this k value, maximum k value we see in this preliminary experiment, turns out to be the maximum k we see in the Hawking radiation. So that agrees well. Also, the angle here in the correlation feature that we're going to see in the Hawking radiation agrees with this preliminary experiment. The angle gives the ratio of the phase velocities outside and inside the black hole. Also, the rate at which the waves are created is consistent with the Hawking temperature that we're going to see in the main experiment. So let's get to the main experiment where we move the horizon at a constant speed. Then the correlation function looks like this. And here you can see this band, this narrow band coming out of from the middle where the horizon is. And these are the correlations between the Hawking and partner particles. So this is the observation of Hawking radiation, this band. And this correlation function was obtained by repeating the experiment 4,600 times, corresponding to 6 days of continuous measurement to see this weak feature. So we can now ask some questions about this band. Firstly, we can take the cross-section of this band. And so this is the profile of it by integrating along the band. And we can notice that this band has some finite area. And so this finite area, one can show that this corresponds to a thermal distribution, that the population goes like 1 over omega for small omega. In other words, the fact that there's this small band, narrow feature in position space means one has a broad distribution in k space, like a thermal distribution. Also, we can compare with simulation. So here's a numerical simulation. And you can see that the simulation looks similar to the experiment, has this band. The simulation also has these fringes, which are an artifact caused by the way the fluctuations are introduced into the experiment, into the simulation. And the fluctuations are introduced into the simulation well after the creation of the horizon, showing that this is a stationary effect, this Hawking radiation. Now we can measure the population of this Hawking radiation. And we do this by a method which we developed when we were working up to observing the Hawking radiation. So here in this region where we see the Hawking radiation, we compute the power spectrum of the fluctuations, or what's called the static structure factor. And the power spectrum should be proportional to the population plus 1, which is the quantum fluctuations. So this way we can extract this population. So here's the power spectrum of the fluctuations as a function of k. Here's the power spectrum. And the first thing that one might notice about this power spectrum is that it slopes downward as k for lower and lower energies. As k decreases, it slopes downward. This is a sign of quantum fluctuations, because thermal fluctuations, like a Planck distribution, will have more and more fluctuations as one goes to lower energies. So this zero curve is the pure quantum fluctuations, and the difference between the zero curve and the measurement gives the population. So here's the measured population, and the dashed curve is a fit of the Planck distribution, giving a temperature of 0.36 mc squared, where c is the speed of sound, or 1.2 nanokelvin. So this is the measured Hawking temperature. Now, we can now turn towards the entanglement to see that these pairs are entangled. So in my theoretical paper, I explained one can use this very same correlation function to see that the pairs are entangled. One can use this criterion, which one can find in the literature, which is equivalent to the Paris-Horodecki criterion, which says that if the correlations, this is the correlations between the Hawking and partner particles, if the correlations of the pair are strong relative to the populations, these are the populations of the particles, so that delta is negative, then the state must be non-separable. If the pairs have strong enough correlations, it can't be classical. So, and non-separable and therefore entangled. So what we can do, we just need to get these pair of operators here, this quantity, the correlations, but this is in k space. this measurement is the correlations in position space. So all we need to do is take the Fourier transform of this correlation feature, and that the Fourier transform of the cross section of this feature here along the x double prime direction gives us this pair of operators that we're looking for. However, we made an assumption here. We've neglected these other pairs of operators. And however, these pairs of operators are correlations between waves of different frequency. So in other words, it had all these operators, all these pairs of operators contain negative k's. That means wave k's directed with the flow. Due to the Doppler shift in this flowing condensate, a wave directed with the flow has a very different frequency from a wave directed against the flow. So therefore, this partner particle, for example, has a different frequency than this minus k wave over here. And it's difficult to think of what would correlate waves of different frequencies in this system. Hawking radiation certainly wouldn't. So we can safely neglect these correlations between waves of different frequencies and neglect these terms. And it's actually been proven recently that if the system is stationary, the correlations between waves of different frequencies are exactly zero. So in other words, this method of measuring entanglement is not a general method for measuring entanglement. It's taken advantage of this specific system where we have the inhomogeneous flowing condensate. Furthermore, we can see that these variables are non-commuting since these correlations don't commute with these populations. It's sometimes considered good to measure entanglement by measuring non-commuting observables, although it's recently been proven that one actually doesn't need that. Okay, so now, so what we want to do to see the entanglement is, here's the profile we said of this feature here. We want to take the Fourier transform of it and square it and plug it into this delta criterion. So here's the Fourier transform squared of that feature, and here's the populations. And we can see that the correlations are above the populations for a wide region of k. The solid curve is above the dash curve, and that corresponds to entanglement. And we can take the difference between the solid curve and the dash curve, and that gives us minus delta here, as in this delta criterion. So minus delta, so every place that this is positive corresponds to entanglement. We also see that these correlations agree at high k with this light gray curve. And this light gray curve is the limit given by the Heisenberg uncertainty principle. There's a maximum amount of correlations that there can be due to Heisenberg uncertainty. So in that sense, this curve, the measurement is maximally entangled for very high k's, and that it's consistent with this gray curve. For lower k's, however, we can see that the curve is very much below the gray curve, so it's much less than maximal entanglement seen, and no entanglement seen below some k value. So furthermore, we can see that the curve ends exactly at k max, which was that maximum k seen in the preliminary experiment. And also, here's the simulation, and it also ends at k max. So it's qualitatively similar. Here, the agreement with this maximal, since this maximal entanglement criterion was computed using the population, beta squared is the population, this agreement here shows thermal behavior up here at the highest k's. So we can ask, how statistically robust is this observation of entanglement?
Yes. So why is this curve shifted with respect to K0 by this equation?
Which one? Which curve? The gray curve.
Yeah.
Why is it shifted relative to what? K0, K0, K peak. K0, K0.
Which is the explanation of
Okay. Which curve? Which it's shifted relative to the solid curve or the relative to this dotted curve? Do you mean? Yes. I don't know which one.
So you write down the Hawking temperature?
That's over here.
Okay. So
Okay. This curve, it's actually quite an amazing thing. Okay. Why? This is, some theoretical prediction, you could say, for the Hawking radiation. It's well above this this curve over here, which is the population. And that's why there's entanglement, because this curve is above this curve, you can say. And how much above should it be? Well, anyway, it's given by this formula. But anyway, so this curve is above this curve, so there's entanglement. And this is a very, very strange thing, because this is the population. The population is essentially goes exponentially to 0. Yet, there's entanglement. Let's consider some high k up here, around here. The population has gone to 0, but the correlations have not. So you have correlations between waves which have no population. These waves don't exist, and yet they are entangled. So I hope that answered your question. Sort of. It's not the population. It's calculated from the population. And here's the formula. It's the population times the population plus 1. That's the gray curve.
Okay, so the left curve is just an exponential.
It's, well, a Planck distribution. That's the, yeah, it's the population. Similar to an exponent. So, okay. Yeah. Yeah.
So usually in this side of black holes, the Hawking temperature is the gradient of the horizon.
Yeah.
They're very sharp potential, presumably probes quadratic part of the spectrum, the value spectrum. It's not just a linear formula. Should it actually be thermal in this distribution, or there should be some corrections to it? And
Yes, there are corrections. So, if you look, when I said the fit of the Planck distribution, here's the fit of the Planck distribution. You see how it has sort of a weird shape here and suddenly cuts off. That's the non-exponential part due to those high k's beyond the linear regime.
I see that.
Yeah, there's a cutoff here.
So what you see is consistent with some theory that is irrelevant to your experiment.
Yes, but I don't know if I could really differentiate between this curve and, say, some slightly different curve. But you see these error bars here.
Okay.
But it, yeah, you're welcome. However, you could say it's very much, what we see is very much in agreement with that preliminary experiment. Meaning the K distribution, this Hawking radiation, cuts off exactly where the outgoing waves, which we've created with a piston, cut off. So we really seem to understand the modes which are playing a role here. So we can ask how statistically significant is this Hawking radiation, is this measurement of entanglement. We can ask, due to noise, maybe this population is really way over here, where it would no longer be below the correlations, and there would no longer be entanglement. However, here's the measured power spectrum. That would correspond to this 2.7 nanokelvin curve, which is ruled out by many standard deviations by the measurement. Another possibility for no entanglement would be these correlations would actually be to the left of the populations. So that's, in other words, maybe this wide K distribution, really due to noise, is really a much narrower K distribution. That would mean, in other words, this narrow-looking feature that you see here is maybe actually a very wide feature. So here's the profile of the feature. It would need to be wider by 90% for there to be no entanglement. But the width, given these error bars, is known plus or minus 16%. So the entanglement is confirmed with a significance of 5.7 sigma. So in conclusion, quantum Hawking radiation is observed. And the Hawking radiation is observed through the correlations between the Hawking and partner particles. The quantum nature of the Hawking radiation is verified by observing the entanglement. The experiment is well within the quantum regime, characterized by spontaneous emission and entanglement, since the 1.2 nanokelvin measured Hawking temperature was much less than the 2.7 nanokelvin temperature, which we saw was the limit for no entanglement. The measurement shows maximal entanglement at high energies and no entanglement at the lowest energies. Thermal behavior was seen at very low energies and also at very high energies. Low energies due to the finite area of that feature. And at the high energies, it was due to the agreement with the Heisenberg limit. The oscillating horizon experiment, the preliminary experiment, verifies the Hawking temperature due to the rate at which the excitations were created. It also verifies the ratio of the Hawking partner phase velocity, since the angle of the feature here in the plane was the same in the two measurements. And it also verifies the width of the Hawking partner correlation feature due to that maximum k. The simulation verifies the approximately stationary background on which the Hawking radiation occurs, as well as the width of the Hawking partner correlation feature, again, due to that maximum k. So what are the implications of this for real gravity? What did we learn about real black holes from this work? Firstly, we learned that black hole thermodynamics is verified experimentally, at least in the analog sense, in that an analog black hole does radiate, and this confirms Hawking's calculation. Furthermore, the Hawking partner pairs seem to be entangled, and this confirms an important element in the discussion of information loss, because as I mentioned earlier in the talk, this limits the outgoing information available. Thank you.
So you said the Hawking temperature is 1.2 nanokelvin.
Yes.
What is the temperature of the bosons?
Okay, it's lower than I can measure. I developed this technique of measuring the condensate by looking at the power spectrum of the waves, and that gives me a result of a 0.1 of the chemical potential or less for the temperature, and so it's below what I can measure. Whereas the Hawking temperature is about 0.36 of the chemical potential, so it seems to be well below the temperature, well above the temperature. Yeah. Yes.
Could you infer now from this Hawking temperature the mass of this analog black hole? How massive is it in your experiment?
I see. Okay.
Because there's
Yeah.
this formula.
Yeah. This formula. Right.
Where the mass is inverse proportional to the Hawking temperature.
Right. Okay.
So
Well, the way I would answer that is the mass determines the radius of the real black hole. And then once you know the radius of the real black hole, then you get the Hawking temperature. The wavelength of the Hawking radiation should be long compared to the diameter. It's really just a classical scattering problem. If you have some sort of a index of refraction, change in index of refraction, that scatters wavelengths which are long compared to the sharpness of that wave. So you can say somehow the mass of the black hole would be given by the wavelength of our Hawking radiation, which is a few microns in somewhere around 10 microns in length, if I remember correctly.
And the mass would then be
Ah,
how large?
okay, then you want to convert that into okay, so then
I'm just
once you,
wondering.
yes, so if you have a black hole of diameter 10 microns, I don't know what the mass of that black hole is, but you would then have the issue of if you want to use the speed of sound or the speed of light. If you compute MC squared, okay, if we could,
Maybe we don't have to force ourselves.
yeah.
I was just wondering.
I would guess, okay, it'd be MC squared. 1 nanokelvin is 20 hertz. So somewhere in the order of magnitude of 20 hertz of energy, 20 hertz times Planck's constant. That would be the mass of the black hole, I guess. Not very much.
You mentioned some simulations and then also showed that there were some artifacts due to. Can you say a little bit more about the simulation? What kind of simulation is it? Is it truncated Wigner, and where do the artifacts come from?
It's okay. It's, for those who don't know what truncated Wigner is, it's a Gross-Pitayevsky simulation, which where one adds in. Gross-Pitayevsky simulation doesn't include fluctuations, so one adds them in. Instead of doing truncated Wigner, I did an experimentalist version where I simulated an experiment where I put the fluctuations in, which was easier for me than putting them in by hand as in truncated Wigner. So it's sort of a, but it should be approximately equivalent.
So it's Gross-Pitayevsky, and then you, okay, so, and then how did you put them in? Or
Okay, I simulated this, we developed this technique of putting, okay, one turns on a random potential for a very short time. And this potential should be properly filtered, this random potential, so it gives the correct zero temperature distribution of fluctuations. And that's the same distribution of fluctuations that the truncated Wigner gives you. However, when you turn on a random potential for a short time, you end up with these pairs, making pairs. So I start out with my correct distribution of fluctuations, but they're paired in two directions, and that's what gave me those extra correlations that I didn't really want. The truncated Wigner doesn't have these pair correlations.
What does this equal to horizon compared to the Technion?
Compared to the healing length? It's a few healing lengths. Let's see. We could go back and see that here. Yeah. Yeah. Okay. Here you could see this is in units of healing lengths, and this is the zoom in on the horizon region. So you see it's about 2 healing lengths.
But then it's Hawking radiation temperature is not applicable.
The Hawking radiation what?
The calculation of the Hawking radiation temperature is not applicable in this region.
Yes, the temperature would not be given by the formula. In other words, if you took the slope of the, well, first of all, it's not that bad. But anyway, if you took the slope of this, the speed of sound, if this were a very small slope, one can take the slope and get the Hawking temperature that way. But once the slope starts to be shorter than the healing length, you're limited by the healing length determines the Hawking temperature, not the slope. So yeah, it's not in that strict analogy, but it's not so far actually. You could almost use this slope to get the Hawking temperature. It'll give you Hawking temperatures only a little bit too high.
Can I ask some naive question? I'm not so familiar with this, the language of this Hawking radiation. But it looks to me this is in a moving frame. You have a kind of incident matter wave, okay? And then you see some Hawking reflections. There's some transmission, some reflection due to the barrier. Would this be how I should think about why the transmission reflection are correlated?
Actually, that's not really the correct picture because you can consider it as stationary. If you have a step potential and a condensate flowing over, you can have, there's a solution to the Gross-Pitayevsky equation which is purely stationary with no waves or anything, which will last forever. However, due to the quantum fluctuations, you then get some waves appearing. So it's not like you're not really scattering the condensate off of the potential in that sense. You could think of the condensate as stationary with no waves. And then these waves appear. Would be a better way to think of it.
The measurement was done in the kind of when the system reaches some kind of equilibrium or stationary.
It is. It does. Yeah. It will continue. Here's the profile of the density. It will continue like this for a fairly long time. This is actually why we use this waterfall potential. We discovered that this is a great way to accelerate a condensate to high speeds without making any excitations. If there are other ways, for example, if you push a condensate over a bump, that up at the top it'll get accelerated to high speed, but as soon as you get 1% above the speed of sound or something, you're going to get all sorts of waves. So we were able to go to something like 4 times the speed of sound without getting all sorts of waves. We don't see any waves appearing due to this technique of the step potential.
Okay. Another small question. So when you see the correlation, why is correlation negative?
Okay, that's
These are the 2 dark lines.
yeah. It's predicted to be negative in the theoretical papers, but to give you a hand-waving explanation for why it's negative, I could draw what it looks like. I mean, it means that but it's not. I don't have a really good answer to your question. I'll just draw what it looks like. It means that say here's the horizon. It means that one of the sine waves is coming out like this, and the other one is coming out like this. This is the pair. This is the horizon. So they always come out with this, this correlation as I've drawn it, that one is positive and one is negative, but one goes down. It doesn't go like this. That would be a positive correlation. So that's all I can really say about why.
So you write down all your correlations and and your correlators for the equation and relation operators for your phonon.
Yeah.
But what you measure are the densities.
Yes, yes, the densities.
Now, when there are approximations going to from the density to the
Yes.
thing, so
That I mentioned. Yes. Okay.
so how do you get directly from your density measurement to the operators?
Okay. What one does, one uses from the density of the operators, one uses the Bogolubov approximation, in which case the density at a given operator at a given k is proportional to these just annihilation and creation operators at k and minus k. So, so that's the first step, is the Bogolubov approximation. Okay, I know. So then one calculates this product of each of these operators here is proportional to b of k plus b of minus k. Well, one of them is an annihilation operator. And then when plugging in here, then one gets a sum of 4 operators, which and then I neglect a bunch of them. Yeah. Wherever that was. No, it was later. So I don't know if that answers your question.
Yeah, because if you want to make measurements of the phase,
Yes.
if you want to relate the measurements of the phase to the equation and relation operators of your phonons,
Yes.
they are only related if you make certain approximations, which means you will neglect density fluctuations. You cannot neglect density fluctuations. You cannot neglect directly the measurement of the phase to the equation and relation operators of the phonons. Now the question was, do you come up with, do we have some similar things here? Because I never did the calculation for the
Okay, so say again, you can't.
So if you really want to do, we do all measurements in phase.
Yes.
And relate to them to the phonons and the correlation
Yes.
function of the phonons. For that to be true,
Yes.
there are certain approximations in there. So that what I write down in quantum field theory, the correlates I write down in quantum field theory are the ones that are really measured in the experiment.
Okay.
One crucial approximation I have to do is that I can neglect density fluctuations. Yeah?
That makes.
And so the question is
I
that
don't agree.
you have something similar to do here.
I don't agree.
Because
Okay.
you have density fluctuations great to the equation.
I don't agree. One needs to measure. When he needs to, first of all, one has to make the Bogolubov approximation, which means you have small amplitude waves. That you need to do. Then, when you can then quickly show that one has quantum fluctuations by the commutation relation of the operators. When this plus 1 here, these quantum fluctuations just comes out from the commutation relation of these operators. So if you, for some reason, for whatever your application is, I guess you're throwing away what comes out of the quantum.
No, we see that plus 1, say, in the realization experiment,
and those are quantum fluctuations
at plus 1.
And furthermore, in a Bose-Einstein condensate, the quantum fluctuations are really quite trivial and definitely there. In a Bose-Einstein condensate, vacuum fluctuations is just the fact that it's composed of point-like particles, which is undeniable. One would never say my Bose-Einstein condensate is not composed of point-like particles. As in outer space, the vacuum fluctuations are something more mysterious. You can say somehow empty space is not really empty. That's vacuum fluctuations. But in a Bose-Einstein condensate, there's no doubt that there are vacuum fluctuations. It's merely the point-like particles that compose the underlying condensate. So I don't know. We could discuss it later so I could really understand exactly what the question is. But
Okay, let us thank.
one more. We have to hear Martin's question.
I just didn't.
That's okay.
Just gave me the idea that it would be interesting to do time of flight, in which will be strongest and very fast in the radial direction, so that you can see the phase in time of flight, which, who knows, might be very sensitive.
Good idea. Interesting idea. Yes.
Okay. Well, thank you very much.